Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan, and I am a chemical engineer. Today we will discuss heat exchanger innovations. We have discussed basic concepts of heat exchanger and air cooler design and operation in earlier videos. From time to time, various innovative ideas to improve the basic shell and tube exchanger or air cooler design have been developed. During our seminars, we are often asked for comments on the feasibility of using one or other of these assorted designs. Therefore, dear gentlemen, in this video we offer you our comments regarding a variety of attempts at heat exchanger and air cooler design innovation that have been developed over the last 50 years or so, such as smooth high alloy tubes, low-fin tubes, sintered metal tubes, spiral heat exchanger, tube inserts, twisted tubes, helical tube support baffles. You should be cautious, whereas all the designs we include have found some successful applications. The key to success here is to find the right application, and as ever we will add the further cautionary note that the best approach is most often to copy a successful application or design rather than to innovate. Therefore, dear gentlemen, please use caution when attempting to use any innovative designs or applications where they have not already been used with success. Ask around if you have an idea to improve heat exchange on your process unit. See if you can find someone else who already had success with the same approach. Smooth high alloy. Tubes' use of smooth high alloy tubes in otherwise corrosive service has been widespread practice since the 1950s. Tube metallurgy is selected to minimize corrosion while in service. The tubes therefore maintain their smooth, shiny finish. Without sites for fouling deposits to attach or accumulate, the clean heat transfer coefficient is maintained. This idea has been used with success in refinery catalytic cracker feed preheat service, placing slurry oil on the tube side and vacuum gas oil on the shell side. Caution: to prevent galvanic corrosion of the tube bundle, the entire tube bundle should be constructed of the same metallurgy. This would include the tube support baffles, tube sheets, and tie rods. We also note that while there is an obvious advantage to maintaining smooth, shiny tubes for applications in sensible heat transfer, this may not be true if it is necessary to vaporize liquid in the exchanger. Some operators have experienced difficulties due to film heat transfer resistance and lack of nucleate boiling sites when attempting to use smooth tubes to vaporize relatively pure component liquids. This would be true for high alloy tubes or simply new replacement bundles for bundles of lesser metallurgy. Low-fin tubes. The low-fin tubes are made by machining grooves into the exterior surface of the tubes, which increases the surface area by 2.5 times. The use of low-fin tubes is not a new development. It is an idea that was in common use in the 1960s with mixed results. A successful application is the use of low-fin tubes in clean propane refrigerant condensing service, with clean cooling water on the tube side. Observed heat transfer rates increased by about 70%. However, if the controlling resistance to heat transfer is on the tube side, the increased outside surface area of the tubes does not improve heat transfer rates. Caution: if the shell side is subject to fouling, then dirt gets between the fins, in which case the heat transfer will now be worse than with smooth, unfinned tubes. Sintered metal tubes. The development of sintered metal tubes dates from the 1970s. A rough coating is applied to the exterior of the smooth new tubes. The hottest fluid is on the tube side. Boiling is intended to take place on the shell side or exterior of the tubes. This is only useful in flux-limited situations when boiling relatively pure components and when heat transfer rates exceed 10,000 BTU per hour per square feet. In such circumstances, the sintered metal tubes act like boiling stones by the way in which they provide sites to initiate nucleate boiling and thereby overcome flux limitations. The application of sintered metal tubes is limited, and, in some applications, they are either unnecessary, not beneficial, or really should not be used. For example, do not use sintered metal tubes in the following applications. If exterior of tubes is slightly corroded and pitted, then there are already plenty of nucleate boiling sites. if a sizable portion of duty is in the form of sensible heat rather than latent heat. If fouling on the shell side is significant. Spiral heat exchanger. The spiral heat exchanger concept represents a completely different type of construction as compared to heat exchangers or coolers with tubes or tube bundles. In this quite different design, there is only one channel per medium, thus the design aims to eliminate the possibility of channeling and suppress fouling. The objective of the design was to produce an exchanger suitable for heating or cooling of slurries and other process streams containing solids and/or fibers. Spiral heat exchangers are constructed by winding two long strips of plate metal around a center to form a spiral body, which then contains two concentric channels. Each channel is welded closed at alternate sides, shown picture. Covers are then bolted over each side of the spiral body to complete the unit. When both of these covers are removed, the entire surface area of the exchanger is available for manual cleaning. Spiral heat exchangers have been used with success in refinery fluid catalytic cracking (FCC) unit service to cool the main fractionator bottoms product, where they have proved to be less subject to fouling than other types of exchangers. Although one client commented that they had needed to make awkward repair welds between internal channels. In general, we are informed that this type of exchanger can be constructed of any material that can be cold formed and welded, such as carbon steel, stainless steel, high nickel alloys, or titanium. We are also informed that this type of exchanger may be used at design pressures as high as 430 PCHE or in vacuum service, and at temperatures as high as 750 degrees Fahrenheit or as low as -40 degrees Fahrenheit. Alfa Laval produces this type of exchanger. Tube inserts. We are aware of three different kinds of tube inserts, but all three are based on the idea of a metal spiral inside the tube. The commercial names are Spiral, Turbo-Tal, Fixotal. Spiral was originally developed by ELF Research, whereas Turbo-Tal and Fixotal were originally developed by Total Research. Spiral and Turbo-Tal are the products of independent research programs launched by ELF and Total in the 1980s, with the primary aim being to reduce fouling in crude preheat exchanger trains. All three of these tube inserts are now marketed by Petrochemical, shown in picture. Spiral tube insert. The spiral tube insert is a metallic coil stretched over the length of the tube and held in place at each end by straight wires. In operation, when fluid flows through the tube, the spiral coil vibrates axially and radially. The concept is that this vibration reduces fouling and increases flow turbulence, producing an improvement in the heat transfer coefficient. However, there is also an associated increase in tube side pressure drop of about 3 psi per pass at tube side velocities of 3 feet per second. The main applications for spiral so far have been oil refinery preheat trains for CDU, VDU, FCC, water treatment feed exchanger HTS units, and high tube velocity applications as found in reboilers. Turbo-Tal tube insert. The Turbo-Tal tube insert coil, also referred to as a helicoid mobile, is designed to rotate within the tube. This is achieved by a mechanism at the tube inlet that holds the Turbo-Tal insert in place but allows it to rotate. The velocity of the fluid in the tube determines the speed of rotation. There is also some micro-vibration of the coil within the tube. The concept is that the tube side fouling rate will be reduced by continuous scrubbing of the tube wall and also have a favorable impact on heat transfer. The associated increase in tube side pressure drop with this device is about 1.5 psi per pass at 3 feet per second tube side velocity, about half that of spiral or Fixotal. The main applications for Turbo-Tal so far have been in the preheat trains of oil refinery CDU, VDU, FCC units, and water treatment exchangers. Maximum tube side velocity up to 7 feet per second, but cannot be back flushed or sustain reverse flow for cleaning, as that would unhook the Turbo-Tal coil. Fixotal tube insert. The Fixotal tube insert is a metallic coil, which is static and self-tightening inside the tube. There is no intended mechanical cleaning effect with this insert. The concept is to increase turbulence in the tube side flow, especially at the tube wall, by constantly mixing slow-moving fluid near the tube wall back into the bulk, thus increasing tube side heat transfer rate and reducing fouling. The additional tube side pressure drop with the fixable insert is about 3 psi per pass at tube side flow velocities of 3 feet per second. The fixable inserts have been used in single and two-phase flow applications, that is, condensation and evaporation. Only the fixable inserts are used in air coolers and are intended to reduce fouling, particularly with paraffin coating or water cooler scaling. We also note that fixable has been used in U-tubes and can now be left in place during hydro-blasting for cleaning. General comments on spiral, turbotal, and fixable tube inserts. In some of the early spiral and turbotal installations, although there was initial reduction in fouling rates, there were also problems with mechanical integrity of the tube inserts. Broken pieces of the tube inserts were all too often found in pass partition boxes of the heat exchangers. We have been informed that improvements to the design of spiral and turbotal were made to combat these problems, and apparently the end results are favorable, although we note that the life expectancy of the turbotal inserts may be a 2-year maximum, whereas spiral and fixable have up to 5 years service time. Naturally, these tube inserts may be attractive as retrofit items, with potential savings in energy costs and reduction of downtime for exchanger cleaning, but it is important to be careful when selecting these, as with any piece of equipment, to be sure that the tube inserts are appropriate for the service for which you intend to use them. Note that both spiral and fixable can withstand back flushing for cleaning, but turbotal cannot. Petrochemical now has over 30 years experience with the design, installation, and operation of these types of tube inserts. There is also standard service offered by Petrochemical from initial valuation to select the most favorable type of insert to suit clients' working conditions, economic evaluation of projected savings, insert manufacture, supervision, or, if preferred, management of installation and monitoring of performance. When these inserts work well, they work very well, but sometimes they are selected for an unsuitable application, just as in the case of the particular air cooler that we described below. It is clearly most important to carefully evaluate the suitability of the service that you intend to retrofit, consult and work closely with manufacturers of the equipment, ask around and seek out other similar applications to compare performance of the retrofit in the field. You cannot fight heavy fouling service with these inserts. The metallurgy of coil and corrosivity of fluid must also be considered. Air cooler retrofit. In a used motor oil reprocessing facility, the vacuum tower precondenser consisted of a large fin-fan air cooler. Inlet conditions were 260 degrees Fahrenheit and 80 millimeters of mercury. Due to the contaminants in the used motor oil, this is a potentially very fouling service. Tube inserts, called turbulators, basically wire springs, were installed in the fin tubes by the manufacturer. The initial performance was reported by clients to be good. However, 18 months later it was observed a high-pressure drop, 20 to 30 millimeters of mercury, through the air cooler vacuum precondenser. Client reported to manufacturer that they had attempted to clean the tubes by hydroblasting but could not establish a water flow through the tubes. Extract the wire spring turbulators from the tubes, but without any success. That is, the springs were stuck. The air cooler bundle was then replaced with an ordinary fin tube bundle. The use of wire inserts in fouling service, where extra pressure drop is totally unacceptable, represents poor engineering design practice. This is especially so when the controlling resistance to heat transfer is going to be on the air side of the precondenser cooler. Wire spring turbulators may have an advantage over tubes with no inserts in that they keep the tubes cleaner. This seems to work best to prevent fouling if it is as a film. If fouling is in the form of particulates in the feed, then the tubes have a tendency to plug. There is also the effect of increased pressure drop to be taken into account when considering tube inserts as a retrofit. However, the decrease in temperature gradient between the tube wall and the bulk fluid may work well to reduce fouling when the fouling is tube wall temperature dependent. This was seen particularly on a furfural unit when a fixed tube insert was used on the rundown cooler and reduced the storage temperature by about 54 degrees Fahrenheit. Twisted tubes and twisted tube bundle. The concept starts with the use of a tube that is itself twisted, the idea being to promote turbulence within the tube because of the tube wall shape. When you look at one of these tubes, the shape is like a large hollow drill bit shown in picture. These twisted tubes are then arranged in such close triangular pitch on the tube sheets that they are actually touching each other at many points along the length of the tubes shown in picture. One might think that to have the tubes touching would cause a problem with shell-side fouling, but the manufacturers claim that because the points of contact occur on the curved ridges of the tubes, rather than being a problem, the points of contact actually increase shell-side turbulence. The manufacturers also claim that because of all these points of contact, they are able to avoid the use of baffles for tube support and therefore eliminate problems of vibration. Tube vibration in traditionally designed shell and tube exchangers, particularly at the point where the tubes pass through the tube support baffles, can cause the tubes to fail and leak. The other basic concept that is essential to the functioning of a tube bundle made with these twisted tubes is that in manufacture of the bundle, the tubes must be grouped or lined up in the bundle so that the ridges do meet and touch to form the curved points of contact described above. Also, and most significantly, this alignment produces shell-side cleaning lanes at various angles all the way through the bundle between the ridges on the tube surface shown in picture. Various advantages are claimed for these twisted tube bundle exchangers. Reduced fouling due to increased turbulence on both shell side and tube side. Increased heat transfer as a result of increased turbulence and lower fouling rate. Reduced pressure drop as compared to traditional shell and tube heat exchangers, both shell side and tube side. Increased heat transfer capacity as a result of around 30 or even 40% increase in surface area as a retrofit bundle in an existing shell. This extra surface area is achieved because the tubes are so tightly packed. Elimination of the risk of vibration because of each tube being tightly locked into place by its 6 immediate neighbors, and also allowing greater velocity than traditional shell and tube exchangers. Use of a shroud around the bundle inside the shell allows the use of existing inlet and outlet nozzles. A shroud that incorporates an impingement plate can be made in 2 pieces that bolt together for ease of removal during bundle cleaning operations. Smaller shell size on new equipment as compared to traditional shell and tube exchangers. We have heard that these exchangers have been used in a variety of oil refinery applications, both in horizontal and vertical exchangers, some of which include semi-regenerative naphtha reformer feed effluent exchangers, where reduced pressure drop brings additional benefits, increasing the hydrogen recycle ratio without changes to the recycled gas compressor. Hydrocracker. Hydrotreating, feed reactor effluent exchangers. Alkylation units, both on sulfuric acid, feed reactor effluent exchangers, and hydrofluoric acid units. Crude preheat train, with crude on tube side or sometimes on shell side. Use of twisted tubes. Twisted tubes are used in crude preheat with crude on the tube side. The main benefit that is found seems to be the increase in surface area, typically 40% more surface area in the bundle since there are more tubes in the bundle compared with a conventional bundle that would fit the same shell. Actual experience shows that the twisted tubes may foul more readily and will plug if fouling deposits are from particulates in feed. But the twisted tube design does work in this service to combat fouling if deposits are formed as a fouling film inside tubes. Special techniques are required for tube side cleaning, but cleaning the tube side is not any more difficult than cleaning conventional tubes. At one refinery, on a 180,000 BSD crude unit, 2 parallel, 6,000 square feet, titanium twisted tube bundles have been in service for a number of years. Crude tower overhead vapors plus steam are condensing on the shell side. Crude is on the tube side. Fouling on both the shell side and the tube side appears to be quite minimal. However, the heat transfer coefficient is bad, only about 20 to 25 BTU per hour per square feet per degree F, even when the exchanger is clean. We attribute this mainly to the relatively low, 3 feet per second, tube side velocity in cold, 50 degrees Fahrenheit, somewhat heavy, 25-degree API, crude with a high viscosity. The overall performance of these exchangers did not improve all that much, according to our client, after the new twisted tube bundles were installed. However, they also converted the exchangers from 4 to 2 tube side passes, and this decreased the tube side velocity by half. Presumably, the reduced tube side velocity offset the benefits of the twisted tube design. Converting back to 4 passes is difficult, because the tube ODs are so tightly packed with twisted tubes, and there is very little space to accommodate additional new pass partition baffles. Twisted tubes with the crude on the shell side. We have heard of a few applications of this. We note that if fouling deposits are particulates in the feed, this appears to be a bad application. General problems and concerns with twisted tube exchangers. The main concerns seem to be, is it going to plug up, and are we going to be able to clean it? The answer is that in general people find it is possible to clean both the shell side and tube side following manufacturer's guidelines, time period and method, and using fairly standard cleaning equipment. However, there have been instances when cleaning has been difficult or even impossible. Special care should be taken on acceptance of a new twisted tube bundle to verify that the tubes are lined up correctly and that all shell side cleaning lanes are unobstructed. We know that although there is concern as to how to clean these twisted tube bundles, in some cases, the run length has been so long that even years after installation there still has been no need to clean the bundle. Apparently when it works well, it works very well. Other problems and concerns with twisted tube exchangers have been the need to take extra care when pulling and reinserting the bundle because, especially with the surrounding shroud, twisted tube bundles are less robust than traditional shell and tube exchanger bundles. The need to take more care when commissioning twisted tube bundles in extremely hot service because they are less rugged than traditional shell and tube exchanger bundles, and there may be a greater risk to tubes being pulled out from the tube sheets by uneven thermal expansion. The cost of the twisted tube bundle as compared to a new larger traditional shell and tube exchanger of comparable surface area with wide rotated square pitch for ease of cleaning. In some cases, the traditional shell and tube exchanger, shell plus bundle plus installation, was the least expensive option. Putting crude on the shell side of a twisted tube bundle may cause problems with fouling. Do not put vacuum reside on the shell side with twisted tubes. Twisted tube bundles are manufactured by a division of Coquelich and are also marketed by Brown Fin Tube in Luxembourg and the United Kingdom. Helical tube support baffles. Tube bundles with helical baffles are now produced by both ABB Lummus Heat Transfer and Coquelich. HTRI now has a rating for this type of design option in their software. Although the traditional shell and tube heat exchangers have segmental tube support baffles at 90 degrees to the line of the tubes, the helically baffled tube bundle has tube support baffles sloped so as to induce a helical flow pattern on the shell side shown in picture. The concept is to ensure effective bundle penetration and avoid dead zones so as to leave no stagnant areas where shell side fouling could accumulate. Also, helical baffle plates can be spaced to reduce unsupported tube spans, without affecting pressure drop or heat transfer characteristics, to mitigate flow-induced vibration. The designers also claim that the helicoidal baffle arrangement permits increased heat transfer. We have heard of helical baffle exchangers being used in oil refineries to preheat delayed coker feed with vacuum resid on the shell side, with the helical baffles. In this service, the helical baffles seem to work well, resulting in less fouling, slower rate of increase in pressure drop, and better maintenance of heat transfer coefficient as compared to traditional shell and tube exchangers. These effects have proved consistent over several years. Another example from oil refineries is in crude preheat service with vacuum resid again on the shell side, with the helical baffles. Once again, similar results are seen as described above, with less fouling, reduced rate of increase in pressure drop, and better maintenance of heat transfer coefficient as compared to the conventional shell and tube exchanger design. Our more direct experience of this comes from current practice in the United States, but we have also seen evidence of similar applications in Australia, as discussed in a recent article on the subject of crude preheat exchanger train redesign. We have also heard of a case where a heat exchanger was retrofitted with a helical baffle bundle and the shell side fouling actually increased. The client theorized that being as how the angle used to slope the baffles can apparently be varied by the designer according to service conditions, the angle for the baffle had not been correctly selected. In general, helical baffle tube bundles are most cost-effectively used as replacement bundles in existing shells. However, for this to actually improve heat transfer rates, the controlling resistance to heat transfer must be on the shell side and not the tube side of the heat exchanger. Basically, this means that the shell side flow must suffer from some combination of high viscosity, low velocity, high rates of fouling, low available pressure drop. For an equivalent shell side delta P, the helical baffle will be less fouling and will provide less film resistance and less fouling resistance than will a conventional vertical tube support baffle. In summary, the helical baffle design will not help improve the performance of a shell end tube heat exchanger if the controlling resistance, fouling or film, is on the tube side. That's all, gentlemen. If you like my video, please follow my YouTube channel Petro Intelligence.